so we're going to deal with circuits, in fact, that look like, eventually, let's just jump to one example of what we're talking about here. So, for example, this circuit. It's got 2 EMFs, it's got 3 resistors, it's sort of parallel looking, but it's a mess. Bottom line is it's a mess. And so you really can't consider it strictly parallel, strictly series, but you can still figure out how much current, for example, is running through the various branches and through the various resistors. We can figure, our goal would be to figure out how much current is running through this, and actually which direction is it running in. We don't even know. And there's ways to determine that. And the way to determine that is using something called Kirchoffs Rules, or laws, I think rules, probably. And there are 2 of these to keep in mind. So what we're going to do ultimately is use these 2 rules that are up here to come up with multiple equations. So as you well know, let's do this. As you well know that if you have 2 unknowns, so like an x and a y, 2 things you don't know, how many equations do you need? 2 equations, right? In order to solve it, you need as many equations as you do unknowns. So, like, for example, you might recall something like 3x plus 2y equals 17, and, I don't know, negative x plus 5y equals 11, and there's a few different ways you can go about solving this. You can substitute. In this case, it's really set up for multiplying everything in the bottom equation by 3, so that I would get 3x, 3 times 5 is 15, this would be 33. And then adding the 2 equations together, which will make these go away, give me 17y equals 50, and y would be 50 over 17. And then, of course, I would plug that back into one of the equations and find out what x is. So that's just one method for doing this. Of course, what if you have 3 unknowns? How many equations do you need then? Take a wild guess. You need 3 equations. So, and so forth and so on. If you have as many equations as you do unknowns, you can find the unknowns. And so we're going to use these rules to come up with the number of equations necessary to find the various, usually it's the currents that we're finding. So, the rules. 2 forms, 2 rules. One's called the junction rule, that one's called the loop rule. We're going to look at each one thoroughly before we, and how we can use them to create an equation. It's just a quick summary of them. Let's start off with the loop rule, because it's the easier of the 2, I think. So we've already really looked at the junction rule. When we were talking about parallel circuits, and we talked about how when current comes to a parallel section, that whatever the current is coming in is going to break up between the 2, and the 2 currents, so little I1, little I2, they've got to add up to what you came in with. You're not going to lose charge, right? If a river comes and has to split around an island in the middle of the river, you don't get more water flowing by per second. Or less, it's the same amount. It's just in 2 different streams. So that's really all the junction rule is you can't have more current coming out of a junction than you can going in, or vice versa. Whatever goes in has to come out the same amount. And so let's look at that before we start really looking at the loop rule. And I'm pretty sure these come up again. So, conservation of charge. There's conservation of matter, there's conservation of energy, and there's conservation of charge. You just can't have electrical charge disappear. And so, if you have a particular junction, whatever the current coming in has to be equal to the current going out. So in this case, you could create an equation that would say I1 has to equal I2 plus I3. That seems pretty straightforward, doesn't it? I mean, like, whatever comes in, got to go out. Right? So junction rule is generally the easier of the two to understand and make simple equations. This current is equal to the two, and you, as we'll see in a minute, the weird part with this is we're going to actually have to guess at the direction of the current. And it won't matter if we're wrong, because in the end, you'll see if we get a negative current, that just means our guess was wrong, but we know the value will be correct. That's one of the funkier things about this. But I don't think this is overly difficult for us. So we get the equation from literally looking at a junction and deciding what's in and what's out after we label the currents. Loop rule. Loop rule's a little more tricky, but still, I think with common sense, I don't know. I have a way of explaining it that seems to make sense to me, so maybe it'll work for you guys too. This is more of a conservation of energy type thing. So, like I said, actually, let me see if I can get the concept of this to you first. Yeah, let's talk about the concept of this first. Loop rule is all about, let's talk about this real quick. Loop rule is all about voltage drops or rises. All right? When you cross a resistor, or you cross, say, an EMF, a voltage source, depending on the direction that you go, you're going to experience a voltage rise or a voltage drop. And we'll talk about how to recognize which one. With EMF, I think it's easy. If I'm considering myself traveling it this way, well, I go from low potential to high, that's an increase in voltage. This little line is low potential, this long one is high potential. If I were to consider myself going this way, it would be a drop. Makes sense. Negative. And it all depends on the direction that you imagine yourself walking this loop. So that's why you choose a direction, you try to stick to that. Here's how I look at it. This is, if you ever get a chance, MC Escher was awesome. This is, I have to give this credit, right? He's dead, but I'm sure he would. I had the good fortune one time of being in the Netherlands with a bunch of 14-year-old boys in my son's soccer team. I mean, don't get me wrong. I wanted to go to Amsterdam in college so bad, I didn't have any money. Finally get there, and I have to chaperone stupid boys. I couldn't just have a good time. No. Yeah, I know this is on screencast, but anyway. Point being is there's a museum with, he was Dutch, and there's a museum we stumbled upon. It's awesome. So, what he was famous for was because drawings are two-dimensional inherently, right? He would mess around with the three-dimensional aspect of it. He would make things that were impossible look real because of this. For example, what direction does that stairway go? Up or down? So, this isn't, here, I'd say up, but wait a second, if it was up all the way, how can you get back to that same spot? Right? This is the what we know is the reason I bring this up. We know this has to be something funky with this, because if you start at a particular location and you walk or do a round trip and come back to that location, like when I go hiking, for example, I know that if I come back to the trailhead, whatever my ups were are equal to my downs, correct? Because what was my net change in elevation? 0, right? I had to have as much, I must have gone up as much as I came down if I returned back to my starting point. Is that? Right, so think about how that works with, the same thing will work for potential difference drops and rises for any loop in a circuit. So let's just consider a parallel branch. So for any closed loop like this, you would see in a circuit, and I'm going to call this resistor 1 and this resistor 2. And I'm going to say, you can actually guess, I'm going to say the current is that way for both. Say this is I1 and this is I2. That arrow represents the current. So if I were to start here at spot A and then go through resistor 1 and then go to B and then C and then through resistor 2 and then D and then back to A. If I was to start here and walk around this loop, all my ups, my voltage rises, have to be equal to my voltage downs. In other words, the sum of them all have to be 0. So let's look at how this works. So, this is you. You're starting here. You're going to go this way. Now, when you get to a resistor, ask yourself, am I going with, in the direction that I'm walking, is that with or against the current? In this case, is it with or against? Which way is the current? I'm going this way. So it's with, right? So I'm going with the current. So the resistor's whole point in life is to turn some of that electrical energy into thermal energy, usually. There's always, if you're going with the current, there's always a drop in voltage. Here's an analogy that should work. If you're going with the current and you get to a waterfall, when you get to the bottom of the waterfall, what has happened to your gravitational potential? It's gone down, right? You've dropped down, right? Make sense? So if you're going with the current, this would be a negative drop. I would consider that negative. And I go around, blah, 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 blah. So I would write 0 equals, and for now, I'm just going to write negative delta V1. Then, when I get to this one, as I reverse, imaginarily walk this loop, when I get here, I'm going upstream, aren't I? I'm a salmon now. All ready to lay my eggs, getting back home. All right, so I can spawn and die. Anyway, I just wonder what they're thinking about with it. Anyway, they're probably just thinking, don't get eaten, don't get eaten, don't get eaten. That's all they're thinking, really. So, fair. So, when they get to when they're going upstream, when they get to a waterfall, right, they have to go up. They raise their potential, don't they? So when you're going against the current, in this case, it would be a positive. It would be an increase in voltage. Now, what about the drop here and the rise here? In this simple example, they have to be equal, don't they? Because it's the only way they're going to cancel out, right, and make 0. Because by the time I get back to here, I need to be at this. I have to be at the same potential. I can't go back to that point and suddenly be at that point. Can't be at a different potential all of a sudden. So when we do the loop, we're using conservation of energy. Says that if you traverse a loop, when you get back to where you started, all of your voltage rises. You can literally think of them as hills, right, or waterfalls. You're going to walk down this waterfall here and reduce your potential. And then you're going to go up an equally tall waterfall here and increase it back to where it was so that your net is 0, your net change. Cool? Yes? Maybe. Okay. So this does not happen because this is impossible. Cool? Okay. So notice, in order to do this properly, I mean just email after email. I haven't checked it in a month and a half. I sat down last night, 526 emails. I got them down to like 260 by just getting rid of spam. All right. Not that that's important in screen text, by the way, I apologize. But, so first of all, I mentioned earlier, first step in this process for the loop rule is you have to pick a direction for the current. It won't make a difference in the end. But you have to pick a direction because if you think about it, where is it? Here. How did I know this was a drop? Well, because I was going with the current. So I have to have some direction to the current. I pick it, really doesn't make a difference. The math will work out. By working out, I mean that if you happen to pick a direction incorrectly, and it's not like incorrect sounds like you're wrong, but if you happen to pick a direction that is opposite the actual direction, no big deal. Your answer for that will come out negative. And you'll use that negative current until you've done the entire problem, and then when it's time to write your answer about that current, you just write it as positive. And we'll talk about the trick of making sure you keep the negative while you're finding other things. Then you pick a direction. I could have easily have chosen to go the other way on this one, right? I could have gone this way. And then this would have been the negative and this would have been positive. But it doesn't matter as long as you're consistent. And they're always going to add up to 0. So as you go, you record the various voltage drops and rises, and so forth and so on. Having seen all that, I think it's best if we just do a problem so we can actually see it in action, shall we? So our goal is to make lots of equations. This is where they discuss what happens when you go with the current. So if I'm traversing it this way, that's going to be a drop. If I was going this way, it actually would be a rise, it would be a positive. Also, notice that because of Ohm's law, another way to look at that voltage drop, instead of writing this, let's say it's a negative drop, instead of writing that, I could write I times R for that resistor. If this was resistor 1, for example, I could write I1, R1. In fact, I probably would, for reasons that we'll see in a moment. But when you see I times R, you're really looking at the change in voltage. All right, real quick about this, once again. In the circuit diagram, the little side is low potential, or negative side, and this is high potential. So if I traverse it this way, it's a voltage increase. If I happen to go this way, as I'm considering it, that will be a voltage decrease. That one's pretty straightforward. You'll see, those are usually easier. Alright. When we're making equations, generally you use the junction rule less often, because usually there's only, you can do it for multiple junctions, but it comes out to be the same equation. You'll see. Alright. Loop rule, boom, boom. Alright. I'm going to do no, this one. I think this is a good one to do. I don't even know what they asked us here. It doesn't matter. What I'm going to find, first of all, we got to label some things. So sketch this in your notes real quick. And here's what I want you to do. First, let's put down the resistors. So this we're going to call R1. This one we'll call R2. We'll call this one R3, which will be convenient because their resistances are 1, 2, and 3 as well. While you're doing that, also mark down, to help us with the loop rule later, and so let's go mark some points. A, B, C, D. I'm just using these, E, F. I'm using these letters to help me describe for myself various junctions or loops that I might try to use. Let's call this EMF 1 and this one EMF 2. Just so we're really clear. I don't think we're going to need to use that. So, what I would recommend, well, first thing you have to do is make a guess at the currents. Now, it ultimately doesn't matter. I somehow have a hang-up where I always try to kind of guess to get it right, but I almost should make sure that I guess them wrong in at least one of the cases, so you can see how we would handle that. So I'll do this. I'm pretty sure that I3 doesn't go that way, but I'm going to put it that way, and we'll see how it turns out. I'll put I2 going that way, and I'll put I1 going that way. So when I say I1 going to the right there, my board is really giving me headaches here. I'm going to recalibrate. 1 second. At this point, I may have all 3 currents wrong. I'm not sure, but let me just clean this up if I can. So when I say I1 is going this way, what I really mean is I1 is actually the current throughout this entire branch, from there to there. So all of that is I1. Where does I2 reign supreme? Well, just between these 2 points, right? From here to here. That's I2. Where's I3? I3 is the current through this whole branch. Okay? So I put it through the resistor, but the truth is it would be anywhere on this branch would be I3. Let me get rid of some of those lines so I don't confuse the issue, though. So, you ready? Let's do a junction rule first. Pick a junction, F or C. Alright, F it is. So we're going to do junction rule on point F. So ask yourself, junction rule says that all of the current all the ins have to equal all the outs. So who are the ins? So coming into this junction, 2 is definitely coming in, and 3 is coming in, correct? So I2 plus I3 equals the outs, which are, there's only one, I1. That wasn't too bad, was it? Now, in this circuit, it would serve no purpose to do the junction rule at C at this point. In your head, take a look at C and decide what you would say. Well, you would say, in that case, 1 is in, right? And 2 and 3 are out, and guess what? We created the same equation, haven't we? And we need, in order to solve for find I1, 2, and 3, I need 3 equations. And these are not 2 different equations. They're the same equation. So the junction rule, in most of the problems you're probably going to end up doing, is only going to use once, really. But it's a shame, because it's the easy one. But so now, what I like to do when I'm solving these is, once I have an equation I think I can use later, put a box around it, remind myself, okay, there's how many equations, how many unknowns do I have? I have I1, 2, and 3, what I'm ultimately after. So I have 3 unknowns. So how many equations do I need? 3. I got 1. Check. Now we have to go to the loop rule. I don't even know what they're asking. I'm not working. Well, we have a choice. We can pick any loop. How many loops do you see up there? How many closed loops do you see? I see 3. One at the top, one at the bottom, right? And the whole thing. So there are actually 3 loops. We will not use all 3, but there are, in fact, 3. There is the one at the top here, right? One at the bottom, whichever way we want to do it, and Let's do A, B, C, F, shall we? Just the top loop. Doesn't really matter. I like to A, B, C, F, back to A. I kind of like to describe the loop. Particularly if you're doing this for somebody who's grading something, make it very clear what your loop you're talking about, so that they can spot any silly mistakes as opposed to ones that represent some lack of understanding. So, and I'm going to do it in that order. So in my head, I'll change to a different color, in red. In my head, I am pretending to walk or swim or whatever you want, this loop, like that. Okay, so the first thing I run across in my journey is resistor 1. Is it a rise or a drop at resistor 1? You're going with the current, right, down the waterfall. So, oh, by the way, we always start with 0 equals. We know they all have to add up to 0. So start with 0 equals. I get to resistor 1, there's a drop. Now, I don't write this down. I don't write negative V1, because I'm after the currents. Instead, I remember that Ohm's law says the voltage drop for any resistor is going to be I times R, right? But I know R, don't I? All right, so this is really 1 I1. I'm going to leave the 1 there as a coefficient to, right? Because the resistor is 1 times the IR, RI, same thing, right? Except, what did I say? It's a drop or a rise? It's a drop, so I'm going to put a negative 1. All right, so negative 1I1 is the drop I get, the delta V at this point. All right, so let's continue our journey. I go through B, I get to this junction, I make a right-hand turn, and bam, I get to this EMF. Do I rise or drop across that EMF? All right, it's a rise, right? And there's no variable there. I just go up 1 volt plus 1. EMFs are easy. There's no variable, just up 1. Assuming you know the EMF. What's the next thing I do? I go down again, so I have negative, and it's 2I2 because the resistance is 2. And then, exactly, that's it. Then I go back to my starting point, and I'm done this loop rule. What I suggest that you do at this point, what I like to do at this point, is solve this equation for put the constant on one side. Because I got 2 i's, I1 and I2, so I can't really do much with it right now. But, see if this makes sense. I can write this as 1 equals I1 plus 2I2. Because if I bring the 1 over here, it'll be negative. But then I can multiply everything by a negative 1, and boom, I got this. So I believe this is algebraically correct. Prove it to yourself if you like. Here, I can do this. I can take both of these, add them to both sides, and end up with 1I1 plus 2I2 on the left equals 1. Is that cool? If I add this, add 1I1 and 2I2, add that to both of those to both sides, it'll be positive when I add them over here. Alright? And then I just write with 1 first. Either way, I have another equation. We get one more equation. We should be good to go. So let's pick another root, shall we? Loop rule. Apply to your call, ladies and gentlemen. What do you want to do?
C, D, E, F.
C, D, E, F. Do the bottom loop. That works for me. You know, I think we should do the whole loop because like you won last time when you picked F. So we'll do the whole loop. There we go. Be fair. So we'll do the whole loop. All right. So that would be A, B, D, E, A. I'll skip. I won't write them all because it'll be clear. So A. Oops. A, B, D, E, A. Whole loop. I'm going to give you a second. And if you're at home, you should pause the video. And you should try to do this loop on your own. I'm going to pause it here while class that is actually present today, tries it on their own. See what they get. Did you pause the video or are you lazy? If you're lazy, shame on you. Well, as I made a mistake, I think that is what we're looking at. Yeah? We go, starts off just like the other one. We go across resistor 1 with the current, so that's a negative drop right there. Then the next thing we encounter is the second EMF, and I believe, go from high, as we're coming around this way, we go from high potential to low, so that's a negative 4 drop. And we drop again here. And that's going to be negative 3 I3. Maybe it's a little cheesy the way they set this problem up with the resistor, but anyway. Resistors and the numbers the same. So, in a similar fashion, I'm going to rearrange this one so that it has the constant on one side, 4. So I'll do an intermediate step. If I add that actually on both sides, take it back here, it's going to be positive over here, equals negative I1 minus 3I3. I'll leave it like that. So I have that equation. I have this equation, and from before, all the way at the top, if I remember correctly, I have I1 is equal to I2 plus I3. So from here on out, we're really looking at an exercise in algebra. You have 3 unknowns, 3 equations. There's multiple ways to attack this. I'm going to do it this way. I'm going to take, so each of these equations has an I1 already. So if I could replace, say, this I2 with an expression in terms of I1 and I3, then I would have 2 equations with just I1 and I3 as the variables. So I'm going to take this, and I'm going to solve it for I2. I2 is equal to I1 minus I3. Now I'm going to take this and substitute it in for I2. With the goal being, when I'm done, both this equation and this one will then be in terms of I1 and I3. And I'll have 2 equations with 2 unknowns, and I'll be able to solve it. So let's take a second, and we'll substitute that in. So I got 1 equals I1 plus 2 times this, I1 minus I3. I'm going to take a second to clean that up. 1 equals equals 2i1 minus 2i3. I distribute the 2. And then you're going to combine the i1s, the like terms. So you have 1 equals 3i1 minus 2i3. I'll give you a second to get caught up. But now I'm going to use this equation and this one to boil down I1 and I3. So sometimes it's a matter of personal preference, but for me, that's what I like doing it. I'm going to take that equation up here. So I'm going to write it down here with, actually, do this. Get rid of this box. I think it's going to be easier. So I'm going to write, well, I got rid of this. What was this? This is a 1, right? Boom. And then this equation right here is 4 equals negative I1 minus 3I3. And so I like this negative right here because I'm going to be able to multiply everything by, in this bottom equation, by 3. And that will enable me to cancel the I1s. So I'm going to rewrite this. 1 equals 3I1 minus 2I3. Don't have to change that. Sometimes you do have to change both. The bottom one, I'm going to multiply everything by 3 and make that 12 equals negative 3I1 minus 3I3. No, not 3, because I multiplied it by 3. And it's going to be a 9. 9. There. And combine. So I got 13 equals, well, these go away, equals 9, 10, 11, negative 11 I3. You might recall at the start of this odyssey that I was attempting to deliberately pick the direction of current 3 incorrectly. Go incorrectly. Just for this moment right here, because you notice what's about to happen. I'm going to divide both sides by negative 11, and I3 is going to be negative 13/11. We can even get that as a decimal. Because this is physics class, not math, so we can do that. Point being is, what's the significance of the negative? That means, is the current really going that direction? No. As soon as you see that negative, we know it's going the other direction. But, my friends, I cannot stress this enough. This is why I wanted to do this. Do not, because what we're about to do, right, is take this number, and we're supposed to plug it back into one of these equations to get I1. Do not make it positive. Don't be like, oh, but I was wrong, I should make it positive. No. The math was all set up. The math assumes this has to be negative. So leave it as a negative until you're done the problem, and then you go to fill in the answer blanks and say, hey, what's I1, what's I2, what's I3, and then you put down positive 13/11 or whatever it is in the decimal. But not until you give your answer. While you're using it to figure stuff out, that negative mathematically is very significant. So we keep it. So I'm now going to plug in negative 13/11 into, let's plug it into, let's go put it into this equation here. So we're going to put that in for I3. Going backwards. So 1 equals 3I1 minus 2 times negative 13/11. I'll stick with the rational numbers instead of the decimals for now.
So because I got a negative, I know that the current is backwards from what I predicted.
Right. It's the opposite. Right. And that's really all it tells you. It's mathematically important for this system of equations. Remember, the math doesn't know you're talking about a circuit, right? It's going to give you a value that works. And in this case, a negative value works, which is why I have to, when I go to figure out the other currents, to get them correct, I have to plug in the negative. Because people see that they were, quote, wrong, and they want to change it, but fix it. No, relax. The mathematical, we're fine. So we're going to make this 1 equals 3I1 plus 26 over 11. Let's see. So I'm going to subtract that. That's going to be 11 from 26 is going to be 15, right? Yeah. So when I subtract that from both sides, I'm going to end up with 15 elevenths equals 3I1. Once again, feel free to go to a decimal. I don't know. But if I subtract 26 elevenths from both sides, it's going to be negative 15, isn't it? Yeah. I'm going to have 1, which is 11 elevenths, positive, minus 26 elevenths, which is going to be negative 15 over 11. Divide both sides by 3, and I end up with negative 5 elevenths. So I1 was wrong as well. What do you want to bet all 3 of them are wrong? So I got let's recap so far. I got I1 is negative 5 elevenths. Don't know I2 yet, but I'm about to get it. I3 I know is negative 13 elevenths. I'm going back to that junction rule and find I2. There's in the junction rule, or at least I'm going to go back to this version of it right here. Focus on that. I'll go back to this one, because this has I2 already solved. So I'm going to do I1 minus I3. Should give me I2. So I2 is equal to I1 minus I3 according to that equation. And let's see, I2 is going to equal negative 5 elevenths minus a negative 13 elevenths. Negative 5 elevenths plus 13 elevenths. That's 8, positive 8 elevenths. So the only current I got right, all these, by the way, should be amps. He says belatedly. Now, what's 8 divided by 11 on your calculator? Let's just check it. So I'm checking. 727. Just curious what the heck they were answering. Yeah, 0.73. That must be the one they were asking for. Was the current through 2. So when I go to give my final answer to this, if they want all 3 currents, at this point I would just write I1 is 5 elevenths. I2 is 8 elevenths. And I3 is 13 elevenths. And you can write decimals once again. And you wouldn't account for the negatives, but you don't do that until the very, very, very end.